Okay, then welcome to our third keynote lecture at this year's IIPF Congress. I hope all of you enjoy this new online experience. It is a great pleasure for me to introduce to you Rick van der Broek as the speaker of the keynote lecture today. After taking a look at Rick's CV, it becomes immediately apparent that he has already taken almost all positions and tasks that an academic and also non-academic person may take. So my introduction of Rick will therefore necessarily be incomplete. Sorry for this, Rick. Yeah, I will take only the most important parts. Currently, Rick is Professor of Economics at the University of Oxford and Research Director at the Oxford Center for the Analysis of Resource-Rich Economies. He is also a Research Fellow of the CEPR International Macroeconomics Program, and he has a further affiliation at the Vrije Universiteit in Amsterdam. He obtained his PhD in engineering at the University of Cambridge. After that, he was employed at a number of well-known and also renowned institutions, like, for example, the London School of Economics, Tilburg University, and also the European University Institute in Florence in Italy, yeah, to name only a few of these institutions. Interestingly, outside academia, he was also very active in the political arena. For example, he was a member of the parliament and state secretary of education, culture, and science in the Netherlands for a period of more than 12 years, I think, if I be right here. So Rick's main research interests are macroeconomics and public economics, with a focus on resource and environmental economics, and there with a particular focus on the economics of climate change, and his keynote today will also be about this topic. He has published over 170 papers in refereed journals. To be concrete, correct, I count them all. It were 172. I hope I don't make a mistake there. Among them, top journal interest journals like the Review of Economic Studies, the European Economic Review, and the Economic Journal, as well as top field journals like the Journal of Public Economics, which is the most important journal for our profession, and also the Journal of Environmental Economics and Management, one of the leading journals in environmental and resource economics. I met Rick the first time at the CESIFO area conference on public sector economics, I think 10 or 15 years ago. He was director of this research area until last year, before he handed over this position to Klaus Kreiner. Rick's dinner speeches at the CESIFO conferences, usually announcing the winner of the distinguished CESIFO Affiliate Award, were legendary, full of humor and funny anecdotes, and always exciting and never boring. So I'm really convinced that also his keynote today will be both informative from an academic point of view, as well as entertaining all the time. So we look forward to this keynote. Dear Rick, thank you for accepting our invitation for this keynote at this year's Congress. We are very happy to have you on the program, and we are looking forward to your keynote lecture with the title Climate Policy, Natural Resources and Public Finance Post-COVID-19. It will mainly be about risk and the carbon price, yeah, and the social cost of carbon, and probably also about stranded assets. Before Rick starts, let me repeat to the audience that you can post questions in the chat already during Rick's presentation. Yeah? So we are happy to collect questions as early as possible. And also one additional information, a secret a little bit, yeah, Rick is the only person, the only keynote speaker, which is in Reykjavik, which is in Iceland, except of the Iceland team. Yeah, so he speaks to you now from Reykjavik. Okay, Rick, looking forward to your presentation. The floor is yours.
Thank you, Marco. This is a very nice introduction, too kind as always. I've been spending the last few week actually traveling for Iceland, and it's an absolutely wonderful place. So I feel very sorry for all of you logging in that you're not here. I keep on talking whilst my slides appear. Very good. I've decided I had a more policy-oriented lecture, but having listened to Ottmar Edenhofer and Ken Palmer, I've decided to switch it for a more technical lecture on those topics. So I'm going to really talk about the risk, both economic risks, climate risks, damage ratio risks, temperature risks, if you want, and how that affects the way we should try to get a grip on global warming and doing some welfare analysis of it. I will look on the one at more an economics approach, which is a kind of welfare-based Pigouvian approach. And then on the two, I will look at the approach which is used mostly by engineering and by the policymaking community, which is very different. It's what the IPCC uses, the International Panel for Climate Change. Then I will move a bit on the topic 3 to finance and why many carbon-intensive assets tend to get stranded. And then I will, if I have time, discuss some obstacles to climate policy and maybe have some remarks, optimistic remarks, and a few remarks related to the COVID-19 situation. So without further ado, I start the lecture with the first part on the risk-adjusted carbon price. This is work with Tom van der Breber, and the aims are as follows. There's a huge literature on these large-scale models of the economy and the climate, and they can be thousands of equations, sometimes they're just 10 or 12 equations. But the beauty of this, what I'm going to tell you, is that I'm going to give you formulas. I'm going to be a simple, well, they may be not simple, but they give you easily to interpret formulas for the optimal carbon price. Now, and the idea is the optimal carbon price is in a Pigouvian sense, you would set it to the social cost of carbon. And the social cost of carbon is just what climate people call the Pigouvian price. So the social cost of carbon is the marginal discounted value of all damages that you get from global warming from emitting 1 ton of carbon today. So that's what we're looking for. But the problem is we don't know what the future growth rate of the economy is. All we know is that the future growth rate of the economy is very highly uncertain. We don't know how temperature reacts to the amount of carbon in the atmosphere. We know that there's a lot of tail risk, so they are typically skewed distributions. We know that some of these distributions have a lot of mean reversion, and then we have a lot of damages, and even the damages we're not sure of. So, and then typically we know that these damages may not be very linear, they may be very convex. So the first thing we're going to do, in a little bit, only a few people do that, but it's becoming more common, is to separate. You can't use normal utility functions. So we will use the utility functions, think of Epstein-Zinn, where you separate the aversion to risk from the aversion to intertemporal fluctuations. So relative risk aversion, RRA, is separated from the aversion to intergenerational equality, if you want. So it's the risk aversion is no longer equal to the inverse of elasticity and temporal substitution. These are two totally different things about preferences, and we need to separate them. Otherwise, you can't even begin to kind of to match the data with your model you've got. There are some technical comments here, but mainly what we're going to do is the reason we get analytical formulas is that we use engineering methods. I used them in my PhD, which is unfortunately 4 decades ago, more than 4 decades ago, but it turned out that Tom van der Breem, who is an engineer, is really good at it, and much better than I ever was. And we've managed to get these optimal formulas out, which I will show you. And so you get a lot of insight without having to do numerical simulations. The problem is really that you have to solve otherwise. We are solving them via perturbation methods. Very high dimensional Hamilton-Jacobi-Bellman equations, because really these are all dynamic programming problems to allow for the stochastics, to allow for the uncertain nature, and these are even very challenging, maybe even too challenging, even for the most modern advanced numerical techniques. So that's why we try to come up with approximate, simple formulas, which we're trying to understand with you. So that's our aim. So we're going to have models of the economy, models of atmospheric CO2, models of temperature, and models of damages. I thought some pictures always help, so here you go. And don't look too much at the formulas, because they're not important. But I would like to tell you that, for example, we have fossil fuel. We assume for purposes of today that they are abundant. Coal is abundant. You might say, there's only finite reserves of oil or gas, but let's assume that they're abundant. It's just actually not they're not scarce. That's a fairly not a bad approximation. These technical formulas you see there, that's what we do. You can't really define utility J explicitly. You can only define it implicitly. That's why these are called recursive preferences. And that's the trick you do to separate risk aversion from aversion to intertemporal fluctuations. Well, there are some adjustment costs. So, for example, in the bottom you see an equation. Again, don't look at it. It will be an AK growth model. So those of you know macroeconomics, it's not like a Solo model or a Ramsey model. It's more like a Paul Romer model, where there's endogenous growth. That's why it's called AK. We'll have constant returns to scale at the aggregate level, but not at a firm level. That's given in the Cobb-Douglas production function in the last line. Again, don't look at the equations. It's not important. But what you do see is you see geometric Brownian motion. You see this first process W1. For those of you who have never heard of continuous time stochastic process, think of that as white noise. But really, so the growth rate of the economy is like of white noise. And I will come to that later. We have some adjustment costs for investment. Again, without that, you can't calibrate the model. Again, they are not relevant that much for what we come up with eventually. Then we have something called an Arrhenius law. Arrhenius got a Nobel Prize, but his Nobel Prize was for other stuff in chemistry. But he was also the inventor of the famous relationship between temperature and the amount of carbon in the atmosphere. He was the first one to do that in 1854. So every climate scientist knows Arrhenius. So all you see in that formula there, it's not that important, and you see that the temperature is an increasing function of the amount of carbon in the atmosphere. It's actually a concave function. That's important, maybe logarithmic or concave. The square root of it would do as well. And on top of that, we also allow some stochastic behavior. So if you look at that parameter key to the 1 plus theta key, it doesn't matter what it is, but that's where there it is. So this thing here, that's called equilibrium climate sensitivity. If you think about it, that shows you by how much temperature goes up if you double the amount of carbon in the atmosphere. So if I ask you what it is, it's about 3 degrees. So if you double the amount of carbon in the atmosphere, the temperature goes up by 3 degrees. But the problem is these climate scientists, they don't know it could be 1 degree, it could be 10 degrees. So we have a very skewed distribution. And we model that with the skewness. We model that if key is normally distributed, so if this key is normally distributed, then by making this theta key positive, we make this whole thing skewed with a tail to the right, and we can actually fit the stochastic process very well. We have damages. They are a function of temperature. Typically, Nordhaus, who got a Nobel Prize for this stuff last year, assumes it is a quadratic function of temperature, so theta t equals to 1. But it also depends on some stochastic shocks. Lambda, they don't need to concern you. Don't remember any of the symbols. They're unimportant. But the idea is that the damage ratio, the damage is how much, it's the bite you get out of GDP because of global warming. The amount of GDP that's taken away because temperature is higher. So this is a huge literature on estimating these two ingredients of the model. So we can take a reduced form. You can put temperature in from the top thing, put that into that, and then, okay, you can put the temperature function into the damage function, and then you get a reduced form damage ratio. Again, we don't need to, so you can, because temperature is a function of the carbon stock, then effectively in the reduced form is that the damages depend on the carbon stock. It depends on shocks to the damage ratio and shocks to the climate sensitivity. Leave that at that, and because I want to move away from the maths and get you to get going on the economics. We need a few more ingredients. So you see in the first bullet, again, that the damages, the TFP, total factor productivity, is normally A star, but in climate science, we deduct a percentage D of it. And that's because of global warming. That's what I've been talking about. Then the next bullet shows you dynamics of the carbon stock. So the amount of carbon in the atmosphere. And basically, the more emissions you've got, the more carbon in the atmosphere. So the emissions are F. And there's a phi term there, and that phi term says that there's a slow decay of carbon in the atmosphere. Basically, carbon gets absorbed by the oceans, and the speed at which it gets absorbed by the oceans is given by this parameter phi. So these are all parameters which are very easy to calibrate and are used and loved by climate scientists. There's the second Brownian process, the second normally distributed errors, W2. And that's because this process is fairly stochastic as well. Then we have two, forget the Ornstein-Uhlenbeck processes, you either heard of it, if you haven't heard of it, think of them as AR1 processes. So these are processes in the shocks to the climate sensitivity and the shocks to damages have mean reversion. And that's all there is, and they are two stochastic shocks there as well. So this is the whole model. I'm deliberately giving you it here, and one more final thing, that all these shocks may be correlated. So the reason I went through this in this model to show that it's a reasonably complicated model as it is, but we nevertheless, then we will show you what the optimal solution is when you maximize social welfare, try to maximize the expected value of social welfare, and try to internalize all the costs of global warming. So, here's the question, as I don't need to tell you because all of you are public finance guys. So this is baby public finance stuff. So we are really talking about Pigovian stuff. So the only externality in the world, and this is 99% of climate economics, unfortunately. So they have a lot to learn from you guys listening in. Is that it is the only problem? The problem is a lack of the only externality is the global warming externality. So everybody is emitting carbon. The emitting carbon leads to higher temperature. But nobody looks at the bad effects of temperature on all the other guys. So that shouts out for a Pigovian tax. So that's what we're going to estimate or try to approximate for. So that really assumes that to get the first best optimum, which we're going to give you, to make sure that it fits in a decentralized market economy, we have to rebate the proceeds from the carbon tax in a lump sum fashion to the households. The alternative is just as good. You can have a global competitive market for emission permits. So the idea is that the carbon price will be the same everywhere in the world. If it isn't, we have to adjust, but that's part for another talk. That's not what we're going to do. So the decentralization this way is only possible when there are no other market failures or externalities. So there is no unemployment, involuntary unemployment. There are no distorting taxes. There are no second best issues. All of these would complicate matters. It's a large part of my research, but it's not what I'm talking about today. But it's really a huge agenda there for public finance guys helping out us type of climate guys. So, and I think there's not enough of that work going on. So this is basically the answer, what we're going to get up. So let me talk you through this. So step by step, and I will do it slowly. But basically, you see in the top line, you see the optimal carbon price. And it's basically something proportional to Y. So that's world GDP. Now, why is that? Damages are proportional to GDP, proportional to aggregate output. So really, the carbon price is proportional to aggregate output. The R there, it should be R star, but you might read something else. But the R star, it shows that it's the present discounted value of all these damages. So that's why you get some interest rate. I will discuss what the interest rate is in a second. And then you see lots of correction terms. 1 plus delta G for the correction term for the uncertainty in the climate sensitivity, delta lambda for the uncertainty in the damages, and delta CK is for the beta term, so that the fact that maybe various climate uncertainties are correlated with the rest of the economy, and there's another one to do with correlations between various forms of climatic uncertainties. So I will propose to you to discuss each of these terms in a go. And I will start with giving you, explaining to you this rate of interest, this discount rate that you need to use. It's a big, if you're a finance guy, then you know this stuff. Then you know this stuff should be fairly familiar. So we're going to really talk to you, what's the risk-adjusted discount rate? So I've decided to kind of separate out that bottom equation in the following way. So it's really, you can rewrite it, as I've given it up here. So really it consists of a lot of terms. The last term is just a decay of atmospheric carbon. Because if there is decay of atmospheric carbon, so if it gets absorbed by the oceans, well, probably then the effect on temperature of atmospheric carbon is less because it dissipates. So then the interest rate is high and you need to price carbon less. So the global warming challenge is less the more decay there is of atmospheric carbon. The problem is that the decay rate has been slowing down because the oceans are getting more fully saturated with CO2. And therefore that term has become smaller. And therefore the interest rate, the discount rate is smaller. And therefore the price you need to charge carbon has become higher. The challenge has become higher. So that's the standard climate science term. Maybe more complicated models, but that's roughly what it is. Then on the very first term, it's a term called time impatience. So that's the more impatient you are as a policymaker, well, the higher the discount rate and the less you care and the less you price carbon. So Bill Nordhaus had a time patience rate of 1.5%. So he really didn't price carbon very much, whereas Nick Stern of the Stern Review had a time impatient of 0.1%, because he believed that was the probability the Earth comes to an end. So therefore, Nick Stern had a much lower discount rate than Nordhaus, and therefore he came up with much higher carbon prices. So that's the first term. Now the second term is the term that you all know if you've done macroeconomics. It's familiar from the Keynes Ramsey rule. So really it is to say the idea that if the growth rate of the economy G0 is very high, then future generations are very rich. And then you say, when you're sitting here, you say, well, bugger you, if you're going to be so rich in the future, you sort out the climate problem, the global warming problem. So then the rate of interest is higher, and therefore you price carbon less. So the idea is if there's a lot of growth in the economy, expected growth in the economy, future generations are going to be rich, and you're going to sit on your hands. You're not going to price carbon as much. That gamma is your aversion to intertemporal inequality, intergenerational inequality. So if you have a lot of aversion to intergenerational inequality, then that effect is even larger and you do even less. Yeah. Then there is a term called the growing damages term. Well, that's just to do with the fact that typically in the formulation I've chosen, and which is in 99% of the models, is that damages are proportional to GDP. So if GDP is growing very fast and damages are growing fast, so therefore the discount rate is lower and then you price carbon higher. Then the other two terms, the next prudence term is, I think, familiar to all of you listening in. We can call that the Sandmo term. The Agner-Sandmo term. It's the prudence term, because Agner did one of the first papers on that. And that's to show the effect that sigma k squared is the volatility of the growth rate of the economy, the long-run growth rate of the economy. Eta is your risk aversion, and gamma is your aversion. 1 plus gamma is your coefficient of relative prudence. So this is exactly equal to the Miles Kimball, is the guy who did this, and Sandmo. These are the two guys. And basically, if you're prudent, it's better safe than sorry. So you're going to be more prudent, the more risk averse you are, and the more prudent you are, and the more volatile the economy. And you're going to have, then you're going to have an even lower discount rate, and you're really going to price carbon. So the prudent thing is to price hell, better safe than sorry. The last term I have to explain, and then we've got a lot of economics in one slide, I think, is that insurance term. Now, what on earth is that? So the insurance term is the idea that if you look in the future state of nature and the economy, maybe 50 years from now, if the economy is suffering a big damage shock, then typically the economy is doing very well as well. So that means you're kind of self-insured. So that means that your discount rate is higher and you need to price carbon less. Again, these are familiar terms in finance, but I wanted to set it up here. So here are the 1, 2, 3, 4, 5, 6 key ingredients of the risk-adjusted discount rate. So all the economic risk comes in here, but all the climate and damage risks come in separately, which I will discuss with you in a second. So when you have a detour, for example, what you could have assumed that if you take a finance approach, they would say that damages are not proportional GDP, but maybe they are proportional. There's a beta, which is called here theta D, that the damages, the elasticity of damages with respect to GDP may be less than 1, maybe a half. In that case, a small elasticity of damages with respect to GDP acts to decrease the insurance term and thus induces a lower risk-adjusted discount rate and a higher carbon price. So when the damages are, say, not proportional GDP, but are maybe just additive, then the self-insurance term drops out, and then you need to price carbon much more. Well, then it goes on a little bit about that. This is, again, very similar to what you see in finance. So let's talk a little bit about the climate sensitivity damage risk. Again, ignore the first bullet with those terms. So I will tell you what it is. So if you have climate sensitivity uncertainty or climate sensitivity volatility, remember climate sensitivity is the response of temperature to the carbon stock. Then we see that it only pushes up the carbon price if the relevant distribution is right skewed or damages are more convex. So the effect on the carbon price is largest if the climate sensitivity is very uncertain, the distribution is very skewed, so the tail risk really matters, and climate sensitivity shocks are more permanent and less temporary. So that's the first result you get. It's basically an interpretation of that top left-hand formula. Now, if we look at the top right-hand formula, again, we don't, the correction term for the carbon price for that, we see that damage volatility only has a direct effect on the carbon price if damage shocks are skewed. Interestingly, there are many papers who do this numerically, hours and hours of overnight running the computer. And then they find that if they have symmetric damage shocks, that there is no effect on the carbon price, small effect. But actually, it's exactly zero. So you really only get an effect of damage ratio shocks, uncertainty, if the damage ratio uncertainty has tail risk, if it's skewed. And it's particularly strong if it's more volatile and persistent. Okay, so I would like now to talk about another correction term which appears as well. That's the one on the bottom, that also multiplies up the carbon price. And I think the economists would call it a hedging term. And I will explain the intuition of that in some detail on the next slide. So the first thing I would like you to know that it depends, there's an hedging effect that depends on the risk aversion term, eta, and then there's an offsetting effect due to damage being proportional to output. So we will assume that relative risk aversion exceeds unity, so that the risk aversion is bigger than 1. This is similar to a paper by Derek Lemoine in 2020, which just came out in the American Economic Journal, except he doesn't give the formula. He just conjectures these results. But let's try to show you then what this equation means in words. So here it is. So let's just think on our feet and let's forget the math and let's try to get the economics right. So suppose that in future states of nature, asset returns are negatively associated with temperature. Well, then what I would call the temperature beta is negative. And it pays to invest more in fighting global warming and push up the social cost of carbon. So think of it in this way. So if you have industries selling winter garments or heating systems, they will have a positive beta. So if then they will have a negative beta. But for industries producing wine in Sussex, the beta is positive. Because if the beta is positive, it means that it's easier to produce wine and champagne in Sussex because of the higher temperature. So these industries will do better. So they have a positive climate beta. And therefore these guys say, no, the global warming is fine. Don't price it so much. So it's only those guys who have a negative beta that they don't like this global warming because it puts them out of business. You can't sell your Icelandic jumpers anymore. So if you're selling Icelandic winter jumpers, they're beautiful, I can tell you. I was very tempted to buy one. Then you're really screwed because of global warming. So then you really want to fight global warming and push the social cost of carbon. That's exactly what this formula on the bottom says. But this rho KG is the correlation coefficient between economic shocks and climate sensitivity shocks. And that's what is very closely related to the beta I just mentioned. So the next one also works like that. So suppose that in future states of nature, 50, 100, 200 years away from now, asset returns are negatively associated with the damage ratio. Then the damage beta is negative and the social cost of carbon is pushed up. Again, the opposite may be true as well. So half of me comes from Holland. And Holland has very strong industries who make money from other people's misfortunes. So if you get a huge flood, all the Dutch industry goes out there and they put in strong water defenses. So their betas are such that they are positive. So these guys in the Netherlands, they're happy with global warming because it's more business for them. So that's in a very childish way, I'm trying to interpret this formula again, because that second term with the rho k lambda is the beta for the damage ratio. So that's the novelty. So people have seen this numerically. People have speculated on the importance of e bigger than 1, but here's an explicit formula. So really, when we solve the optimal policies, we literally do it on the back of an envelope. Okay. There's a final thing I would like to mention, and you probably find it strange, but when I gave this talk to climate scientists, this took me 2 hours, this slide, because I said, well, there may be correlation coefficients between the uncertainty in the climate sensitivity, the response of temperature to the carbon stock, and the damage shock. Here we see that if they're positive correlated, they'll push up the carbon price. Again, it depends on how skewed everything are, so the formula is given there. But the point is, this led to deep philosophical issues, whether this should be modeled or how it is modeled or how this comes out of the different climate scientists. So this is really for the climate scientists rather than for the economists, but it has clear economic consequences. So I'm going to show you now in a kind of macro-ish way how to calibrate what I just said. So this slide, again, don't read it too much, but all I want to say here is that we're not calibrating this to past fluctuations in the carbon stock and emissions, because they're very small. The effect will be zero. But we'll calibrate to the uncertainty in the projections of the IPCC, of all these climate science models. These are models with tens of thousands of equations. They're huge number, they're published, and we calibrate to the uncertainty in the future. But that's going to be relevant. So here are the numbers. You don't care what they are, but we've estimated it. I think it's easy to show it in the picture. So there's a paper by Michael Golosov, which most of you will know, and Per Gruzel, and John Hassler, and Alex Javinsky in Econometrica 2014. And their model is the blue one, the blue line on the left panel. Our model is the red line. It's much simpler. We only have a one equation model, but it's stochastic. And we feel we actually fit the stochastics, except perhaps in the first few years, but we do not do a bad job. The proper one to use is a paper by Engenheister et al. Or Joos et al. I'm also a co-author of the Engenheister one, so I know how to do it. But that's 4 differential equations, whereas the blue one is only 1 differential equation. We can allow for that, but for ease of exposition, let's just focus on what we've got. So let's just look at the left-hand panel. That's the impulse response function. I would like, and the gray shaded area is the area where you basically is the uncertainty range, the 95% uncertainty range, and this is what we fit. Now this is the thing what we fit for the climate sensitivity. The left panel shows you what happens after roughly 40 years. So if you double the carbon stock, where's the temperature in 40 years? So you see the temperature increase, it's much less, it's only about maximum 0.9 degrees. This is a probability density function. On the right-hand side, it shows you the long run, the steady state temperature response. And again, you will see that it's rather than around 1.5, it's a bit higher, it's more like 2, 3 or whatever. The blue line is the line fitted by Pindak, which is a gamma distribution, which has been used a lot. We fit the red line, and I think our line fits excellent. The black line is the data, and our red line fits both the stochastics and the thing very well, and that's what we fit, so that's what we use. And if you then look at the IPCC, and we look at the transient climate response TCR and equilibrium climate sensitivity, our calibration does almost suspiciously well. It does extremely well with relatively very few parameters. So that's what we're going to use. And then finally, we have these damage ratios. Bear with me, they show stochastics. This is Nordhaus's work himself. It looks a bit messy, but basically we are fitting the red line model. That's our model. And then we have these 95% confidence interval, which are the dashed red lines. And that's what we will use. And the data we have, all the studies are these bullets, these circles, where Nordhaus was a bit cheeky, and he gave those studies which he thought were empirically very good, a bigger bullet and a bigger weight, and those which he thought were a bit shitty, I won't mention the authors, got a smaller bullet. It's quite a harsh study if you're one of those small bullets, you feel small. But done by a Nobel Prize winner, so we accept that. Okay, so the rest of the model, what you see is we have a risk aversion of 4.3. It's calibrated to US stock markets. We have an elasticity with temporal substitution 2/3, which corresponds to inequality aversion of 1.5. The rate of time patient is very high. I'll talk about that later. Annual asset volatility is about 12%. We have a risky return on assets of 7.2% and a safe return of 0.8%. Okay, it's now about 0. The difference is 6.4%. That's the risk premium. So we fit the data not too bad. We could fit it even better if we had disaster shocks, which I will normally do, but we left it at this. We've got a trend rate of growth, slightly too optimistic now. I would make it lower now, but say 2% per year, and a few other stuff. So here's the stuff. So here's some results. And again, to get those numbers, it was really very easy. You just can do them by hand. So there's no big computers. So let's first look at the base case market-based calibration. It's 6.6, very low. Why is it so low? Because if you fit to market data, you're going to have very impatient investors with this high discount rate. So that means your discount rate, risk-adjusted discount is going to be quite high. Your price of carbon is going to be quite low. $6.6 per ton of CO2 I think is too low. Notice that some people start temperature at its equilibrium level. You see that we show that if you do that, you estimate it twice too high. So that's the second column. And there are also many studies which assume there's no mean reversion, but most of the hit comes much later. So if you assume that the temperature immediately responds, you estimate a much too high price for carbon. So these are just warnings against studies in that literature. So look at the right panel where you have an FX-based calibration. So let's assume then that the discount rate is much lower, say like what Nordhaus says, 1.5%, rather than 5.8%. You immediately see that all the risk-adjusted carbon prices go up. So it becomes 39.8, say 40. And then you see below, you decompose all the risk components due to economic risk, growth rate uncertainty, under 63%, due to uncertainty about the temperature response, 41%, due to uncertainty about the damage ratio, 43%. So the total risk markup is 247%. So you see so you actually price up the price of carbon by a factor 2.5, just to allow for uncertainty. So ignoring uncertainty is a big mistake. It's really bad. So if you now look at this, there's another thing what most people do. If you look at the left panel and the right panel, the left panel, the 39.8 is what I left you with. That would be the one I would go for. But many people use not asset return volatility, but they use the volatility of the GDP growth or of consumption growth. But we know that consumption growth and GDP growth are very smooth. There, the volatility is only 1%. Annual volatility is only about 1.5% rather than 12%. So then, of course, if you use that volatility, which some studies have done, then the risk-adjusted carbon price is much lower. So the markups are much lower. So it matters a hell of a lot which one you use. The model I've used, one of the weaknesses is that asset return volatility and GDP growth volatility are the same. Empirically, they're not. So we're working on a model where dividends are not proportional to profits, to consumption, but dividends are a leverage claim on consumption. And then you can allow for these differences. So here all I want you to look at the last column. If you assume very convex damages, Martin Weitzman, who has recently died, used exactly those damages. He was a very big guy in climate science. But if you use his stuff, you get a risk-adjusted carbon price because of the convexity of $141 per ton of carbon, much, much higher. And if you then look at the last slide, these slides allow you, well, let's not discuss this, but this allows for these correlation coefficients to vary between -1 and 1. And then you look at the effects of correlated shocks. All I want to show you that they go in the same direction as my formulas, as they do, of course. So let's pass on this from the point of time. So you will ask me, which number should I take home? I will ask you to, then I will tell you, take the last. So I like Nick Stern with his low discount rate of about 0.1%. Yeah. And I also like AS12, which is basically Ackerman and Stanton and Weitzman, who have these very convex damages. well, then you get a huge risk-adjusted carbon price of about $165 per ton of CO2, much higher than we have at the moment, factor 10 times higher. But I think this is also what comes out of almost all stochastic models when they don't. I've not used tipping points. I've done it on different occasions, but if you use the best paper using tipping points, a paper by Kai and Lodzek in the Journal of Political Economy of this year, they come with these very high prices of carbon as well. But we start with 6 and we end up with 165. So most of the job is done by ethical preferences, not following Ramsey's rule. Ramsey's advice, ethical advice, is unethical to discount the welfare of the future unborns. You don't do it, it's just very bad. And secondly, also taking care of really complex damages. So, what do we do wrong with this stuff? And this is something also for public finance guys. So what we're not doing is that it's basically just the economic growth shocks are serially uncorrelated. So if you have serially correlated shocks to consumption growth, say imagine they're positively correlated, then you know that if you get a big shock now, a positive shock, it'll be a lot of positive shocks later. So instead of optimistic or pessimistic or positive, yeah, it will return back. This is mean reversion. So if you have a positive shock, it will come back. So you have pessimistic, it's high now, but it will come back to its equilibrium. So these make future consumption riskier and magnify the precautionary term. They curb the discount rates and really increases the cost of carbon, the price of carbon. And this effect is particularly very large for larger horizons. So this effect is also larger the more autocorrelated the shocks are. So we're working on a formula which we have now to allow for serially positively correlated shocks. Nobody does this in the literature, but this is an important point. Now, the second bullet is the point Weitzman should have got a Nobel Prize for. He never got it, but he should have got it, I feel. And that's basically an application of Jensen's inequality. So you could look at the solidity equivalent value of the social discount rate. So I give you there how it works with a gamma distribution, but let's give you a toy example, which I use for second-year students. That's this one. So let's assume that discount rate is 2%, 4%, or 6%. We don't know. We have to give them a probability 1/3, 1/3, 1/3. And then we have $1,000 to start with. Then after 1 year, it's 980. After 10 years, 819. After 200 years, only 18 is left. But if you use a 4% discount rate, after 200 years, only 0.33 is left. And if you use 6% discount rate, really nothing is left. So the discount rate really matters. So if you then look at the mean value of what's left, it gets 961, 679, 184, 52, and 6.2. And if you then back out what discount rate corresponds to that mean outcome, you get a solidity equivalent value of the social discount rates. So it's 3.99, 3.87, all the way to 2.54. So what's the mathematical result, which is true for any distribution, is that last column, the solidity equivalent value of the discount rate, for very short horizons, it's equal to the average social discount rate, i.e. 4%. 3.99 is close enough to 4%. And as you let the horizon go to infinity, it goes from 2.54 all the way to 2%. It goes to the smallest discount rate. So that's the clever result of Marty Weitzman. So that's the idea that you have a term structure for the discount rate. So we can't assume a constant discount rate, you should assume a declining discount rate. So that if you're discounting from period 100 years in the future to 99 years in the future, you use maybe 2%, whereas if you discount from next year to this year, you use 4% or 4%. And that declining term structure in itself leads to even higher carbon prices than I've shown you. So again, uncertainty really matters, and the type of uncertainty matters as well. Term structures matter. It's time to have a rest. So I will now show you, I want to show you what the engineers do. And that's much easier. And maybe, how many more minutes have I got left? I will look at that, okay. So then the question is, why do these IPCC and why do the engineers do this approach, whereas we economists have done this complicated approach I've just explained to you? So now will be, if you were deciding to switch off because it was too much technical stuff, switch on back again, because now you get the easy stuff. And maybe the economists tend to make things too complicated, there where the policymakers want something they can simply understand. So I give you that. Look at this graph. So this graph is perhaps the most famous graph in climate science. So at 0 is Manchester at the beginning of the Industrial Revolution. So that's, and you know, the Industrial Revolution is often taken as a starting point, but from then on people started to burn coal, and that's really when global warming really took off. So really the temperature, when we say 2 degrees, we mean 2 degrees from the beginning of the Industrial Revolution. And then on the bottom axis, the horizontal axis, we have cumulative emissions, CO2 emissions from 1870 onwards. So 1870 in this story is taken as, people dispute when was the beginning of the Industrial Revolution. Here it's 1870. And then the only line that is factual data is the black line up to 2010, very short. That whole orange wafer diagram is the uncertainty done by climate scientists, not by economists. And you see the longest projection is the most pessimistic projection, goes up to 2100. So then the carbon era, the fossil era, goes on to 2100. And then, of course, temperatures go up to 4.5 or 5 degrees, but may even go up to 7 or 8 degrees. So that's business as usual if you just carry on as we are. If you look at the dark blue line, that stops much earlier. The dark blue line is the 2.6 scenario, and that's when we try to limit global warming. So when you look, you draw a line from 2 degrees, which is the target from the Paris meetings, and then you go down to the horizontal axis, you can read off exactly what's your budget. So your budget is about 1,000. You're allowed to emit total cumulative emissions of 1,000 gigatons of carbon from the beginning. So really, you can easily allow for the fact if that budget is, if that line, if you assume, for example, as I assume here, that global warming is proportional to cumulative emissions E, whereas TCRE is called the transient climate response to cumulative emissions. It's about 2. But it's stochastic. So if you fit to that model, just eyeballing it, you can fit a stochastic model to it. You can actually see that if you then look what the probability of that is, if that's a log normal distribution, you can fit what your budget is. But let's look at the numbers. So what we're going to do is, I'm going to compare with you what the engineers do, which is the carbon budget approach, and I'm going to show to you what the economists do. So the welfare maximizing Pigouvian cost of carbon gets the prices out proportional GDP with all these risk reductions I've talked about. The cost minimizing carbon price given the carbon budget constraint is basically, the question is, what should that path look like? So I don't know how many people of you remember the hoteling rule on how fast to deplete oil from the ground. Then typically we say you want the return on keeping a barrel of oil in the ground to be equal to the return on taking a barrel of oil out of the ground. The return on keeping a barrel of oil in the ground is the expected capital gain. The return on taking it out of the ground and putting it in the bank account is rate of interest. So you want the price to increase at the rate of interest. Here it's the same, except the budget, it's the carbon budget that matters rather than how much oil there is in the ground. So all these engineering models had the price growing not at the rate of growth of GDP, but at a risk-adjusted rate of interest, which is typically higher than the growth rate of GDP. So here you see it. So the purple line is the thing that Nordhaus does, and the other 3 lines are the ones you would do when you follow these engineering approaches, and you will find that the more risky it is, the higher the carbon prices, the higher the uncertainty it is. But it's a much faster, and therefore you phase out of fossil fuel much more quickly around 2055 rather than 2095. Nordhaus has been criticized a lot for not being ambitious enough because of this high discount rate. And therefore it takes so long for the Nordhaus model to actually switch out of fossil fuel. So this is just to show you the difference between the Pigouvian approach and the carbon budget approach. So the question then is what interest rate to use for the carbon price. Now, there's a paper by Christian Gollier, and we looked at that, but I mean, most integrated assessment models, most policy advisors suggests a rate of interest between 5% and 12% per year. This is completely ridiculous. It's completely, I call it crazy procrastination. The United Kingdom is the worst of all. They say, let's let the rate of interest rise, be 15%. So they say, let the carbon price rise at 15% per year. That means you take no action now, and all the action is taken later. It's exponential. So it's basically political, just at least to green paradox effects, basically push it to the future. We don't want to do it, let our political successors do it. So Gollier takes a more financier approach. He says, it speaks of the big green bat. So he says the safe carbon budget is uncertain, there's political risk and there's other risks. Future marginal abatement costs are uncertain. And of course, the future growth rate of the economy and therefore the future growth rate emissions uncertain. So he would argue, set the growth rate of carbon prices to the safe interest rates, plus again a beta times the risk premium, where beta is the correlation coefficient between the log of marginal abatement costs and the log of consumption. So he then ends up with a rate of growth in the carbon price of 3.5%, which is much more than the risk-adjusted rate of interest of 0.8%, or 1% he uses, but less than the return you can get on equity. So it's about 3.5%. So you should do less procrastination. It's much more upfront than what most policy advisors have used. Okay, so the question again is that uncertainty really matters for the cost-benefit analysis, even in these engineering approaches, and you have to use the right rate of interest by looking at the risk correction, but you have to look at the correlation coefficient between the shocks to the log of marginal abatement costs and the log of consumption. So I want to slowly come towards an ending in topic 3 and want to talk about peak demand and stranded assets. The more we read newspapers, and particularly now with COVID-19, you think really Shell is dead, British Petroleum is dead, Exxon Mobil are dead. These guys have had their Shakespearean moment and it's only been even quicker. So they faced their life, this was all before COVID, they faced their life or death question. So the biggest fear is that oil demand growth is no longer given in perpetuity. We have some predicting by the end of the next decade and now much quicker, the industry could be facing a peak in consumption as government policy try to curb the use of fossil fuels. No chief executive, no pension fund wants to left holding multi-billion-dollar oil fields the world no longer wants or needs. So that's the next thing we really need to think about. So it's not, it's peak demand is the new peak oil. So we don't have peak oil, we have peak demand. So when you think about it, this is an older study, it's now much worse. We should, they said, if you want to keep it within 2 degrees, you can only basically burn 1/3 of all oil reserves. These are oil reserves which are proven. So people have already invested. Half of gas reserves you have to write off, and you have to 80% of coal reserves. You have to basically write them off. You have to not burn them. So 2/3 of oil, half of gas, and 1/3 of oil, half of gas, and 80% of gold reserves you should leave unburned. If you think it's on 1.5 degrees, it's much heavier. Now the point is, when you go and look in the annual reports of oil companies, I'm not even talking about the national states. It would be the reserves of just the listed companies are 3 to 10 times as much as this carbon budget. So really, that means that these oil companies are either bankrupt or global warming, limiting global warming to 2 degrees is never going to happen. So I've been shorting Shell for a long time, but that seems to be the logical thing, because these things are living death. They're zombies, according to this type of stories. So many climate physicists, they think, well, why are people still investing in them? The answer from BP is, look, these investments, they can just be turned off. We're not actually burning our fingers that much. But not all people in the oil industry agree. So why do these assets get stranded? They get stranded, one, because there is you need irreversible assets, so the investments. So it must not be possible to suddenly change a coal-fired power station into want for making woolly jumpers or anything else. And secondly, it must be something surprising must happen, because if it must be unexpected. So then you might get a stranded of assets. So many people speak of a carbon bubble. So that there is now, of course, many fossil fuel-based stocks and shares are getting premiums of 3 to 5%. So, and that's because investors already recognize that steel assets, aluminium assets, cement assets, oil assets, coal assets are overvalued. They're subject to risk, and therefore they demand a higher compensation, otherwise they wouldn't even hold them. So in that sense, there's a carbon bubble. The carbon bubble, yes, thank you, means that there is a big risk that these share prices of those firms come down. And it's not just in oil, coal, and gas. It's also in those industries which use a lot of fossil fuel, cement, steel, and many others. So, for example, we think of policy tipping. So maybe don't look at these pictures, but maybe the policy tipping is Obama was very good climate, and then Trump comes in and he just says, well, bugger it, I'm not going to do it. And he reversed everything. So that was the other way around, but it may go the other way around, and suddenly a good guy comes in, and maybe Biden will really do a good climate policy if he gets elected. But there's only a probability that he gets elected, however good Kamala Harris is. So we distinguish then 4 types of assets trading. Natural assets that need to be locked up, i.e. the unburnable carbon I've talked about. Capital used in fossil-based industries that become less profitable or economically obsolete. So these are all these steel factories, cement factories. You get an immediate change in stock market prices, the probability, timing, or intensity of climate policy changes. And if the timing and forcefulness of climate policy uncertain, you get an additional change in valuation once uncertainty is resolved. So really, we're beginning to get some papers which look at these types of assets trending. So I'm not showing you this much, but you might see, for example, if there's a policy tipping, and then suddenly Trump comes into power, then you see that the red line jumps up. And that means that the scarcity rent on oil and gas, the monopoly profits of poor old Trump and his cronies really moves up. So that's what happened when he got into office. But of course, and if you look at the investments in exploration capital, of course, the solid red lines are really low. But then if Trump gets elected, they shoot up again and everybody thinks it's party time again. And if you look at the discoveries as well, and if you look at the stock market companies, again, if Biden gets elected, these oil and gas industries, they go down again. And if Trump gets reelected, they get a boost again. So that's the type of uncertainty we need to look at, the volatility we see in markets today and also the uncertainties we see in markets today. So we did a lot of that stuff. There's a paper I have with Humble and Kraft, which redoes everything with a 2-sector model. And then all I want to tell you here, that there is, and gradually coming to an end, that in stochastic case, normally if it's deterministic, you switch the capital to the green sector immediately. But if adjustment costs, the full specialization takes time, you do it slowly. But if it's stochastic, it may well be that you keep open the brown oil production sector for some time as a hedge. Because of course that's bad for global warming, to keep open the brown sector in the sea. But if they really produce a lot of economic output, you might want to open them for some time, because they're paying for the green transition. Then eventually they'll be made smaller, maybe even disappear altogether. Interestingly, if you take the DICE, the Nordhaus damages, they never go close down. Only when you take these Weitzman, these very, very intense convex damages, will you drive the brown sector completely to zero. So what we then see is then you can show the effects on carbon prices, things like that. So here you see that the dirty share of capital, the share of dirty capital goods, fossil fuel intensive goods goes down. We can still do the carbon tax just follows that increasing things. I won't talk about it, but you can look at the risk-free rate of interest and the share prices. I've come to an end. So I've mentioned these stranded assets. Other obstacles are the long timing risk, time scale, and hedging climate risk. That it's very difficult to find assets that yield a high rate of return just when the economy suffers from global warming in 100 years' time. We just don't have those scales. The only thing I can think of are dikes. Third, it's a huge ask, climate policy. It's an ask from current generations. They have to sacrifice for global warming being less 100 years from now. Secondly, it's a big ask because every country in the world has an incentive to free ride. So it's a double externality. It's very complicated. You need pension climate deals, and you need climate clubs on international level. It's the biggest policy failure on the planet, and that's exactly what Extern called it. Otmar already talked about spatial carbon leakage. So that basically this tax incident, so if you price carbon but your neighbors don't, then part of the price of carbon is shifted to producers, so the price of oil goes down. Your neighbors think, hey, the price of oil has come down, so they have a jamboree. They will consume even more oil, and therefore they will emit more carbon. So a lot of your good efforts to reduce carbon emissions in your country are offset by higher carbon emissions abroad. And that's what's called spatial carbon leakage. The thing public finance people could help with this is to have output-based rebates. These are second-best policies, which you can do if you can't use border tax adjustments. You can always do a quotient policy, but that's been spectacularly unsuccessful. The green paradox I've mentioned, that if you procrastinate, then the sheiks say, great. If you say, if you're going to price in the future, I will deplete oil even more, I will emit even more, and that's the thing which is really bad. Policy failure and capture, I don't need to talk to you guys about this. That's your bread and butter business, so I won't talk about it here. The thing I end with is this, and then I'm done. Otmar already mentioned this, that climate policy is typically regressive. It hurts the poor most. So first of all, we should point out that most of the subsidies in the world are for fossil fuel subsidies, a staggering 6.5%. So the first thing we have to do is get rid of those fossil fuel subsidies. But it's about the political acceptability. So what we did is we estimated a complicated demand system, an easy demand system with log linear angle curves. And then what we find is that you get often majority support only if you use part of the green tax reform, if part of the revenue of the carbon tax is used to lower income taxes and boost economic activity in the tax base. You can't give it all in terms of a lump sum dividend, because then it's so bad for the economy, people will stop working, and therefore it's actually counterproductive. So we show that in a table. If you just look at all HH, all households, then if you have a carbon dividend, 32% of households agree to these policies. They get better off. Whereas if you do it with lowering income taxes, 55% of households get better off. But lowering income taxes is quite good, but some of the poorer people will be worse off. So really, what we would argue for, and I have no time to go into this, have a mix of lower income taxes for the efficiency and a mix of a higher carbon dividend for the equity. Again, for all the guys listening in and knowing about Merle's and income tax reforms, this is gefundenes Fressen, so I don't need to talk to you about it. And I leave this, and then we leave to that. To deal with people like Trump and all those people who are climate scepticists, we've done some papers that it's a bit like Pascal's wager. Do you believe in God or not? Well, I've been told, I'm a very Protestant upbringing, and I've noticed I've seen many beautiful churches in Iceland. Well, it's best to believe in God, because you never know when you arrive at Peter at the gates that you want to be able to say, I believed in God, and then you might get a passport to heaven. I think actually not sure about it, because most of my friends will be in hell, of course. But anyway, then the idea, it's better safe than sorry to actually believe, because the costs of not believing are very small. The same thing for climate change. The costs of not conducting climate policy are very small. You just have some Harburger triangle losses if the climate scepticists are right and you are wrong. But if you are right and the climate scepticists are wrong, you lose a hell of a lot if you follow the climate scepticist policy and don't price carbon. So really, you better price carbon. So a max-min strategy, and we looked at many, many examples of that. You always price carbon, and almost as much as you would have done anyway. Thank you very much. Now you can drop it. It's fine.
Okay, thank you, Rick. Thank you very much for this very exciting keynote talk. I like this DSGE model very much. I think it's a very simple model, and you can do many things with the simple model. And I find it impressive that you get this simple formula for this social cost of carbon, where you see all this influences of this risk terms, in order to get some results. And at the same time, you get similar results as other institution gets with much more complex models like the EPCC model, and I think that's really a plus of this model. Thank you very much again. So there are so far no questions. There is a question of Anna Alberini. No, it's not a question. It's only a comment. Very nice, Rick. I hope to be able to see the slides to absorb some of the math. I would like to encourage you to raise questions in the chat. I know it's not the usual way as at a physical congress to get in discussions, but I think that's the only way tractable here. So let me again encourage you to raise questions, which I then can bring to Rick's attention. So I will try to fill the gap in the meantime a little bit with a question. Ottmar yesterday was a little bit pessimistic about the impact of COVID-19. Yeah? So his conjecture is that we have a short-term drop in the emission path, and then this will recover very quickly. Yeah? And I wonder, when I heard your model, I wonder a little bit whether you can map such a shock like COVID-19 in your risk parameters, and whether you can make some statements, also perhaps some quantitative statements about such a shock. And the second part of this question, perhaps, do you think that this COVID-19 crisis will increase the number of stranded assets? So that's more a question to the second part of your talk.
Yeah, very good. Can I use my slides also? So here, it's post-COVID. Are they on there, the slides? So there was an extremely good question. Thank you very much, Marco. The first point is the technical point. You could see the COVID thing like a mean reversion shock.
Okay.
So that you get this bad shock and then things go back to normal again. And that means that it's a bit like these pessimistic expectations that you would actually price carbon more. Actually, and I would agree exactly with what Ottmar has said. Are my slides on now? Okay. So coming to this COVID stuff, I think it's extremely important. So Ottmar made a point that it's all about coal, and he made the point that it's all about coal. That maybe people will use, they will have the targets will be less strong because everybody is emitting less. But therefore, coal will be kept longer in operation. And since coal is relatively more carbon intensive than gas or oil, or definitely more than renewable energy, it actually may be bad news. So I agree on that. But however, there's more to say on this post-COVID thing that relates to your second sub-question. So if you, for example, look at what to do. So I think if you ask yourself the green recovery coming from post-COVID, what do we need to do? We need to have a moratorium on coal. We need to have a moratorium on all fossil fuel subsidies and phase out all diesel petrol-based transport in the next 5 or 10 years. We need a clear price signal, a steady growing path of carbon prices for the next 30 years. Mitigate leakage, so Ottmar talked about it as well. And if you wait, every year we wait, it becomes so much more costly. So the faster you start, the better it is. We need to explain to people that there are many collateral benefits of green. So one, you get less air pollution. And air pollution is a local problem, so that's not so much a set of the free rider problems. But also what we've learned from COVID is that people have learned to have distance conferences. People have learned to work at home. People have learned maybe to live in a less polluting way. So we should try to encourage it. So that means that we should invest in clean infrastructure, efficient retrofitting of buildings, investment in education and trading, natural capital investment, clean R&D, perhaps also governments helping people out to make their offices at home. So give them special subsidies for that. We need to invest in the control of the pandemic, test, track, and contain. We have to invest in vaccines, border checks, and particularly for economists, safe travel and trade. That's going to be the biggest challenge. How do we get the post-COVID area safe travel and trade? How are we going to get food security? And then also the whole thing will be, it's mostly a trade thing. How can we change our supply chain networks and to make them shorter and more local? And and how can we get the sanitary standards so that these supply networks are also up to COVID proof? So we need to invest in renewable energy, batteries, solar, wind, and electrical vehicles, circular economy, and secure ICT networks. And the main thing is to make sure new jobs and sectors are wherever corona-proof. Part-time in offices, part-time at home, less commuting is all win-win. So you want to go towards an economy which is much more resilient. So I would argue this is a citation from one of these reports. Create an army of zero-carbon workers, retraining and redeploying those who can't work into different industries, from home installation to wind turbine manufacturing to tree planting. So the warning is, of course, that it's not going to happen. As soon as we have a vaccine, all the fossil fuel lobbies come in again and will try to frustrate any green plans. So, my big lesson is don't bail out. What's happening now in the Netherlands, for example, is that KLM, and they get huge bailouts. It's the most fossil-intensive industry you can imagine, but no fundamental reforms. So you should only bail out carbon-intensive firms in the pandemic unless they become green. But if they're not, it's a good moment for them to say goodbye to them. So you make sure all firms are carbon-free, can prove that they can capture and sequester all the carbon emissions and overcome all the NIMBY problems.
Okay.
So there's a whole big thing I would like to say to Marco with post-COVID, where the government is very important. There's a spatial planning is extremely important. So what can we bring in from urban economics to make the way we organize cities, the way we organize trade, the way we organize the economy that is pandemic and climate proof. So the golden COVID-19 opportunity is don't keep living zombies from the fossil era alive, but invest in inevitable companies that are going to make the green transition possible. Never waste a crisis. Thank you.
But then you think all these changes have to be infused by the government, if I understood you correctly. Right? So,
yes, or the government has to give the right example by launching customers, having the right policies, and definitely not make it worse. So what's happening now is that they often give those industries which are suffering most are often those industries which rely most on coal and steel to bail them out. But that's just not what you want. You should say secretly have a party, not when they're in the same room, and say, well, this is a good moment to make a big, quantum leap towards the green transition, which is going to happen anyway. And I see this not happening in many, many places. Of course, I'm here in Iceland, and I know that some Scandinavian countries are much better than other countries. But this is the golden moment. We should not waste it.
Okay, there are now some questions in the chat. One two-part question of Waldemar Marz. He thanks you for the great talk. And he asked, do you think by rebating carbon tax revenues in a progressive way, we could generate political majorities for ambitious climate action? Or would that be just the first step in dealing with the political economic challenges? If yes, why don't we observe that all the time?
Well, so thank you, Waldemar. It's the most crucial question, the political economy of it all. And I think the public finance scholars have done lots of good work on political economy. In the climate field, we are still beginning. So we have a lot to learn from you guys. So I hope for more joint papers. That's why I said yes for the lecture. So yes, so the first point of Waldemar's question is related to this paper I have with Arman Razai. And there we estimate a fancy AIDS model for almost idle demand system. It's an easy demand system, which is very general. And then we can allow for the optimal way of rebating carbon tax revenue. And the optimal way is partially use the revenue for a dividend, which is very visible, but you must also use it to lower the income taxes, because otherwise it's just too inefficient. Then we have shown already, I showed you a slide where you can get more than half the people agreeing to it. In that sense, that more than half the people will get higher welfare. They get higher utility from that policy. If you just implement a carbon tax and don't rebate it, almost nobody agrees. You will not get a majority at all. Nobody likes that. But if you rebate it all via a lump sum tax, a lump sum dividend, you don't get a majority either. So you need this lower income tax as was just said. That's just the beginning of the political economy. We need to get rid of all the subsidies for fossil fuel. We need to tell the airline industries, get your act together. They are not being taxed. Greenhouses in the Netherlands are not being taxed. The steel industry and the cement industries, they are almost exempted. The only people who really pay carbon taxes are households and small scale enterprises. So, and the reason is that there's these huge political lobbies which are against it. And then the other political economy problem is on the international global stage, where we really need to kind of bribe, we need to incentivize the poorest countries in the world with large forests, not to cut down their forests. If necessary, we buy up their forests, or we bribe them not to cut down the forests, so we keep those carbon sinks. So that's also an international political economy, where after 30 years of international summits, like Paris and Copenhagen, zero progress has been made, or almost no progress has been made. So that's the political economy challenge on the global scale.
Okay, I hope the answers question. The question is answered. Sorry. There's a further question of Mireille. She also thinks that the talk was very impressive, and thanks you. And she asked, what do you think of the risk of technological lock-in, possibly induced by investment and subsidies in specific green technologies that may appear in the future less promising than others?
Okay, thank you, Mireille. That's an extremely important question. So it relates to issues of stranding of assets, it relates to issues of timing consistency. So one of the reasons we advocate a slowly rising path for carbon prices from now up to 2050. So maybe start with 100 euros per ton of CO2 and let it grow for 2% per year in real terms. Is that the business people know where they're at. So now it's changing all the time. It's right what Mireille says. Let me first take it a bit broader. If you've invested because of Trump in brown assets, in oily assets, coal assets, and then Biden comes along and it's all green, well, then you're going to lose your assets. You will get capital losses. You will really get burned with your pants down. You will lose money. So the idea, I think, is what we need is consistent governments. So ideally, I think we need to take the policy for global warming, fighting global warming, out of the hands of governments and give it to a global central bank, carbon central bank. And the global carbon central bank has only one mandate, and that is to keep global warming below 1.5 degrees. And then there is the certainty on which people can plan. It is, of course, true what Mireille says, that if you've invested very heavily in wind power, and it turns out that wind power is very good, it's getting very cheaper, but then in the end it turns out that solar power, which is now so cheap you cannot imagine, and solar power is now so cheap, and imagine that we get similar spectacular progress in batteries, so that you can actually use solar power, well, then maybe wind power becomes obsolete, and then you're stuck with those assets. I would count it as normal business risk. But the policy risk, to do with policy tipping, that you go from one type of policy maker to another, from Trump to Obama, or from Trump to Biden, that's something the market can't anticipate. That's just really bad. So I wouldn't really advocate compensating owners of coal assets, but they will litigate. So a big issue, which we are not good at yet in economics, is that we see more and more papers on the litigation of those dirty industries that have been encouraged by governments to invest in those things. And then a clean government comes in power, and then they take the government to court and say, look, you encouraged me to go to the industry, so now you compensate me for my lack of losses, because I have not really got a full return on my assets yet. So then the litigation issue and what happens in the courts becomes a really important issue.
Okay, thank you. So there's still time for further questions. So if you have questions, post them in the chat. Yeah. I again try to fill the gap with a further question, if allowed. So if I understood correctly, you still have an increasing path of the social cost of carbon. And every time I see such an increasing path, the green paradox of Hans Werner Sinn comes into my mind. He proposed there a few years ago as a solution to this green paradox, source-based tax on capital. And I wonder if a source-based tax on capital, that was his solution. And I wonder whether it is possible to make a pro or con with your model, with risk, with include risk, regarding this capital tax relative, for example, to emission tax or to permit.
Yeah. Okay. So the first thing to say to all the public finance people listening in, that the green paradox is a second best issue.
Yes.
Yeah. So it's really when there are constraints on the policy instrumentarium. So when there is the idea is that you can't tax today, but you tax only tomorrow. Maybe because there are hyperbolic preferences, or maybe because you're just, for political reasons, you say, yes, we're going to do it, but my successor. But in the analysis I did was first best. So then the optimal carbon tax grows, but it doesn't grow too much.
Okay.
And then it's okay. There is no green paradox. However, in a second best world, of course, the best thing is to get rid of these political distortions. But one way of getting rid of these political distortions or mitigating those political distortions is to use this proposal of Hans Werner Sinn, and some people have looked into that. So that maybe but the better thing is to overcome I would say a better thing is to have an institutional reform where you try to get people to agree on international agreement on how much is the carbon budget that comes from the science. And then you just say, this is your carbon budget, 300 gigatons of carbon we are allowed to still burn, give that to the central bank, and they globally then set the carbon price. That's the cleanest. Because whenever you give it to politicians, they will try to postpone it. It's like when every January I go to the gym, and it's £5 to go to the gym, but it's £100 per year. So that's worth it if you go more than 20 times. So I buy my gym membership for £100, and then I only go 2 times. So then I pay a lot of money per go. So then the best thing is, because I have these hyperbolic preferences, and politicians are a bit like that as well. So then that will introduce green paradoxes. But the thing for that is institutional reform. So you could do what Hans Werner suggests, have this tax, but then the question is, why would they impose it? So you have to find some way of tying these guys to the mast, like the central bankers, at least in Europe, are supposed to be independent. So they've got their hands tied to the mast, and they've only got one weapon for one instrument. They use the interest rate to fight inflation. Things are a bit different now. They've got a second instrument, quantitative easing, to look after the economy. But normally you have, like Tinbergen says, N instruments for N targets. But then if you have these second best issues, you normally don't have enough instruments. Or you don't use carbon taxes, but you get green paradox if you use subsidies, or you don't have a good timing. That's also like having a lack of instruments, which is the second best problem.
Okay. Yeah, thank you very much. So there are no further questions in the chat anymore. And we are also running a little bit out of time. If there are no further questions, it remains to me to thank you again, Rick, for this
thank you very much.
Very stimulating talk, and also for the discussion.
These guys here put out all the beer, so I'll have to drink it all on my own with these guys here.
Okay, so that's the reason why I'm hurry up a little bit now.
Okay, thank you very much. I apologize to the audience. It might have been a bit technical, a bit out of your way, but thank you very much for all the questions.
Yeah, we talked about it before the presentation. I think the mix is really good, between policy-oriented keynotes and also some technical keynotes. Thank you also very much to the question in the chat, and Have a nice evening, and I hope to see you again tomorrow back here online on the third day of this IIPF online conference. Thank you very much. See you.
Bye.